The problem is connected to the earring, but that's not the only place where it is used. It is also important for the thinning of the form plate or the form sheet. If you stamp a roll material, you want the thickness to stay as uniform as possible, and you don't want points where the material is much thinner than at other points, because those are likely points where the material is going to break. So the landfall coefficient, in a way, is a measure of how good the material is for that, for having a uniform thinning when you are stretching or putting some other forms of deformation into it. Now, I must mention that for some applications, that is not necessarily the case. I mean, but that is nearly always true when you are forming something from a full roll sheet in all directions. If it is a strip, then it is a different story, and you may want for it to have some texture. But when you are forming the sheet completely in 360 degrees, then you really want more uniform properties. So the landfall coefficient is a measure of that. And essentially, if you consider that you have a roll material, this is the rolling direction, this is the transverse direction. Imagine that you cut a tensile sample at an angle alpha with respect to the rolling direction, and you stretch it, usually 5%, 6%, 10%. You stretch it, and then you measure the strain in the plane of the sheet and the strain across the normal to the sheet. So that, and you make the ratio of those two things. This ratio, epsilon 2 in this direction, epsilon 3 in this direction, is what is called the landfall coefficient. And that is what, when it is different from one everywhere, we are going to plot it as a function of this angle alpha. If it is not uniform, then that tells you something about the formability of your product. So what it means is that if it is isotropic, what it means is that if this is the yield surface of your raw material, then the landfall, an isotropic material will have the normal, which is the strain rate, along the main directions S11 and S22. And deviations from this direction, the normal being deviating from this direction, is a measure of the anisotropy of your material. So the intersection of your yield surface with the axis and looking at the normal at those points is a measure of the formability. Okay, you are going to be testing this, but VPSC can calculate the polycrystal yield surface, and it will generate three files with the polycrystal yield surface. One is called polycrystal yield surface.out, and the other two files contain the normals to the yield surface and the direction of the normals and the direction of the strain rate. For doing, if you want, it's not really for the usual plots, but if you really want to see how much they differ from each other, the normal to the yield surface and the direction of the strain rate. And so you can plot those files, and in this case where we did a 50% reduction in rolling and calculated the yield surface, and another 50% rolling and calculated again the yield surface, and we said that we have hardening in this case. So the first yield surface is here, the second yield surface is there, the material is hardening, and what I did here is to plot these files, polycrystal yield surface with normals and polycrystal yield surface with rates. And if you look here, the black ticks correspond to the normals to the yield surface, and the red ticks corresponds to the direction of the strain rate. So they are not exactly the same. And if you go into the file polycrystal yield surface.out, you have here the components of the stress, S1 and S2. This is S1, this is S2. The components of the stress for all the points that I use to calculate the yield surface. I use usually 32 points. And then it also has the components of the normal to the yield surface. And then it also gives you the angle that these vectors, be it the stress or the normal or the strain rate, the angles that those directions make with the horizontal plane. Okay, so that is information available in this file. For plotting, you will plot for just plotting a clean yield surface. You will just plot S11, S22 versus S11. That is the only plot that you need to do. S22 minus S11, and that gives you all the points, all the points of the yield surface. The other is just extra information that you can plot if you want. So after doing 63% rolling reduction, that is 100% deformation in the normal direction. These are the textures that we obtain for an FCC material, starting from a random texture. Here if you care, you may try to compare the rolling components. You may try to see where the rolling components fall in each of these textures. These are the ideal rolling components, and you can go one by one. For example, if you pick this one is the cubic. This one is the cubic, these squares. So you have very little cubic component in this particular texture. You may want to go to look at these triangles, the upper triangles. The upper triangles are the B component, yeah. So the brass component, and that component is present in the texture. This one is also present in the texture. So those are the plot of those components for the 100 directions and the 111 directions. Now, the code will calculate the yield surface, and it will calculate the evolution of these components, the copper, brass, S, cos, and cube. It will calculate the evolution of these components with deformation. So you may want to check, for example, obviously the S component is the one that increases the most, so it's the dominant one in this particular problem. And in this plot, these are the open circles, so you may want to go look at the open circles and where they fall in the predicted texture. As I said before, the cubic components are defined if the component is within 15 degrees of the ideal value. It is considered that it belongs to that component. Yes, I prefer to do that maybe personally to you, because it has to do with that sigma epsilon is not equal to, sorry, sigma epsilon dot average, the macroscopic one, is not equal to sigma g epsilon dot g average. Now, there is a very well known lemma, which is called Hill's lemma, that demonstrates that this has to be equal. Now, why it is not equal in our case? What happens is, for doing his demonstration, if you have a polycrystal, so you have your grains here. What Hill did, he calculated the integral of sigma epsilon dot differential volume, and he assumed that equilibrium, the gradient of sigma ij or sigma ij comma j is equal to 0. This is the equilibrium of stress condition. Now, this condition he assumed that is true everywhere, at every point in the material when he calculated this integral. Okay? So that means that when you go across boundaries, you have to assume that it is across grain boundary. You have to assume that the stresses vary in such a way as to verify this. The problem is that in our case, our grains verify that with a homogeneous effective medium, that across this interface they are in equilibrium with a homogeneous effective medium, but this is an average medium. It's not the real environment of each of the grains. So that is what gives us homogeneous stress in the grain. But the price that we are paying for that is that when we say that, okay, I'm going to treat every grain as an inclusion in the same homogeneous effective medium, this is not really true if you think of this as being just homogeneous stress here, homogeneous stress here, homogeneous stress there. So you are going to have discontinuities in the stress. And so that is where the difference comes from. It can be quantified. It can be quantified using the interaction equation, and you can prove that there is a minus sign with a, well, I said I don't want to get into that. There is an average of something that you can prove that is positive here, and so this is always smaller than this. And if you look at the stress strain curve, the stress strain file out, in the last two columns of the strain there is work 1 and work 2. There are two columns at the end of that file, that is work 1 and work 2. Well, they are telling you how far you are. These two values are from each other. For example, it's something that we keep track of. So, and as I showed you, as it shows, it means that the normality rule is not going to be exactly satisfied. It's not that bad, as you see. It deviates a bit, but it's not exactly satisfied. Besides, take into account another thing. These are equal dissipation surfaces. We define the yield surface as equal dissipation surfaces. It doesn't mean that when the stress touches this point, you have plasticity. You have plasticity for every stress, because any stress in a rate-sensitive law will give you some amount of plasticity. When you are close to the threshold value, you are going to get more plasticity. But it doesn't really mean that if you are inside here, you're not going to have plasticity. So if this is the criterion to use to do your calculation, I mean, in a way you can say, yes, I want to adopt that criterion and I want to adopt this as the yield surface. But with the polycrystal model, you don't use the yield surface. You don't use you can calculate it, but you really don't use the yield surface to do your calculation of, you apply a certain strain rate, you get a stress, or you apply a certain stress, you get a strain rate. You don't need to go into a yield surface to see what is that value. It comes from the average, from averaging over the grades. So that is an interesting debate, and I really don't. Yeah, as I said, the normality rule is an assumption of continuum mechanics. I mean, they assume that it is the yield surface coincides with an equipotential surface. So you define your potential, you calculate your equipotential lines, and then you say, this is my yield surface. That is a postulate. It's not a fact. I mean, it seems to work fairly well, but for some things. But I don't know. I don't know what the end of the story is there, to tell you the truth. Yes.
The curve that goes with the peak seems to be Lanford for me, and Young's modulus is the one which has the inverted parabola shape.
Come again. This is
so they are labeled differently. That comes out as.
This is Lanford.
Okay.
This is Lanford.
Okay, yeah, Young is the one which goes. Yeah.
Yes, okay. But it is labeled black. So
yeah, black.
And this is interesting because for this particular texture, you see that if you pull in the rolling direction, you get that epsilon 22 over epsilon 33 is very low. So it means that epsilon 33 is much larger than epsilon 22. But if you go there, epsilon 22 is slightly larger and gives you a value slightly larger than 1. So this wouldn't be a good material for forming, really. Certainly not for beer cans, because it will lead to a lot of earring in your cans, no? Yes.
Is it more important that it is uniform, or is it?
Yeah, for some.
Or also that it is low?
No. For some problems, it really depends on what problem you are going to be using it for.
So say making cups like this.
Yes.
Cans.
For that, it is good if it is uniform. Yes.
Okay.
It is good if it is uniform, because especially if you are punching something from a sheet, and you want the material to flow in the same amount from all the sides, and then your thickness remains the same.
Okay.
So it doesn't have to be 1, can be larger than 1 or smaller, but it is good if in all directions the thinning is the same
the
when,
same.
when you stretch your material. This has to do with the following problem. This is plane strain plus shear, that is rolling with friction. Now, when you do rolling, especially when rolling is done using high reductions, you reduce in each passing. You know that in a rolling train, you put your material through several steps of deformation, and in each one you reduce a bit, and you also play with the temperature in order to play with recrystallization and all that stuff. For some processes, they do large reductions in one shot, so they reduce it 15% in one shot. Now, what happens in that case is that the plate is much thicker than the separation of the rolls. And so the plate has to be sucked into the rolls and comes out from the other end. Now, for that to happen, you need friction, because it's friction, the one that grabs the plate and pulls it in. That friction has an effect. The effect is that if this is the center of the plate, essentially the center of the plate experiences plane strain. But as you go towards the surface of the plate, there is the friction creates a shear here, and so superimposed to the thickness reduction, there is a shear deformation. And then towards the end, there is a reversal of that shear. So you shear, and then it starts reversing back, and it ends up being again square. So there is shear and reverse shear. So people have simulated that using finite elements, and it's kind of noisy the way it comes out. But saying that this is a sinusoidal, that the shear obeys a sinusoidal law is a good assumption. I mean, it can be shown that putting the result of a finite element code or putting a sinusoidal law gives you essentially the same results as far as texture evolution is concerned. What happens is, now you have a velocity gradient that, yes, has extension in the direction of rolling, compression in the direction of normal, but has a component here, L13, which is non-zero. That is your shear. So that is L13 is your delta U1 delta X3. So what we did in this case, I didn't put a reference. What we did in this case is we assume that L13 is a certain value 1.25 times sinusoidal value that has an amplitude 1.25. It goes with epsilon 33. So essentially, while epsilon 11 goes like this, L33 goes like that, L13 does that. And we are going to superimpose this to use this as a deformation path in the code. Now, this is not a homogeneous deformation. It changes from step to step. So incrementally, we change the values. So the code can do that if you if the file if the value IVG bar is equal to 1. This means a non-monotonic law, and you have to read that law from a file. And I show what the file looks like. If you go into this directory, example 3 FCC, there is a file that is called rolling and simple shear, and that gives the 9 components of the velocity gradient. I put here only some of them because most of them are 0. So this is L13, and L13 follows this sinusoidal dependence. And this is L11, L11. Remember that these are rates, so the rates are homogeneous L11, homogeneous L33, but varying L13s. And these are the time increments associated with each one. So instead of reading that other file that I showed you before with the monotonic law, now the code will go and read this file. You don't need the other file that I showed before. The code will read this file, and from this file, and this file can be produced by any finite element code. If you want to know what is the texture evolution in a particular place in your finite element simulation, you can pick an element in your finite element simulation, and introduce that into the VPSC code using this format, and you can get the evolution of texture and also the internal stresses in the grains in that particular element, or the hardening of that element. So when you do that, what you get is the following. If you do plane strain, you get the texture that I showed before, just plane strain. But if you do plane strain with shear, you get, as you can see, you get a texture that is a bit rotated here with respect to this one. We get a texture that is a bit rotated with respect to this one. It's not quite orthotropic. It's not quite orthotropic. You can see here you have this component there that is missing at that position. So of course this may be an issue for some forming operations. And if you compare what we had before with what we are getting now for this path, the yield surfaces are slightly different. They are not terribly different, but they are slightly different. This one is a bit more tilted. Lanford coefficients, as you can see, the Lanford coefficient does change with respect to this value. This value is above 2, this value is below 2. Here the anomaly of the Lanford coefficient has disappeared. It comes to be lower than 1. And these curves also turn out to be slightly different. The S component is a bit higher. So you do change your material. And in some processes they use shear on purpose. In asymmetric rolling, for example, is a technique that they use in order to try to homogenize the texture, and so they have the two rolls don't move at the same speed, and so they induce a shear on the material that is being rolled, for example. If you want to plot these results, those are in the files, well, polycrystal surface out, Langford.out, and cubecom.out. All these results. Okay, this takes care of the rolling of FCC. Let me see. We have still about half an hour. I would like to go do the demonstration of these simulations, and I would like you to also run the simulations yourself and see what we get. I'm going to example 3 FCC rolling folder roll, and you copy vpsc8.in into the root directory, into vpsc8. And that is going to run the monotonic rolling problem. I'm running here, the example this is obtained with the affine calculation. You can run it with any of the other interaction assumptions. The affine gives something in between. So now it is running. So it ran the affine simulation 50 steps. After the affine simulation, it ran 36 step, actually 72, but because the yield surface is symmetric, it only does half of it. It runs 36 steps, so one every 5 degrees, in between 0 and 180 for calculating the yield surface, and then it does, for the Langford coefficient, it does 10 steps, so it probes every 10 degrees from the rolling direction to the transverse direction. It does 10 steps. So I would like you to, I don't know if it makes sense to plot the texture, because you have already seen that texture. The texture is the one that we have been showing for FCC rolling a few times already. But I would like you to plot one of the other quantities, like the cubic components, the rolling components, or the Langford coefficient. I'm going to open the Langford file just to see what it looks like. So the Langford file looks like something like that. It gives you the angle from the rolling direction. It gives you the directional Young modulus, because the code by default, because the code reads the elastic constants of the material, by default it calculates the cell-consistent elastic constants every time. So that information is available. And then the third column is the Langford coefficient. Third column is the Langford coefficient. And then these are the three components of strain rate that were used to calculate the Langford coefficient. Now, as you can see here, um, I'm only plotting D11, D22, and D33, and I'm also plotting D12. The reason for plotting D12 is that there is an asymmetry associated with this test. The symmetry gets broken. So you have a texture that that roughly looks something like this. Okay? So it has orthotropic symmetry. But if you now you do a tensile test at an angle alpha, so this is the rolling direction, and you do a tensile test at an angle alpha on this texture, the symmetry of the sample is not orthotropic anymore, because it has, as you can see, it has this strong component here and this strong component here on the sides. So the tendency if you do this is that you probably are going to develop some shear. So this is one, this is the component one, this is the component two. So if you cut your sample, from there, and you pull on it, the sample may want to shear like that. May want to shear like that rather than staying parallelepipedic. Okay? So if it is going to do that or not depends on how long the gauge of the sample is, and the way in which you grip your sample. If you are gripping it on all the surface, and this is short, then you are going to prevent this type of shear. Okay? But the sample wants to shear in like that. This should be the shear epsilon 1, 2. So this is 1, this is 2. This should be the shear epsilon 1, 2. So if you prevent the shear epsilon 1, 2 from taking place, then you need a stress. There is going to be a sigma 1, 2. On the other hand, if you have a very long sample, and you just you have pins here through the hole, and you pull, this part of the sample is going to shear like that, because it is not constrained by the shoulders. So that is an effect of texture. The symmetry of the test and the symmetry of the texture do not coincide. You break the symmetry of the test. The orthotropic symmetry is broken. So that is manifested in the fact that when I plot or list the sigma 1 and sigma 1 2, you can see that the sigma 1 2 is non-zero. You can see that the sigma 1 2 is non-zero over there. And to tell you the truth, I can remember what is the third column. This is an interesting example of how the code can handle the boundary conditions and give you results that are consistent with the boundary conditions that you impose. So if I were to impose a velocity gradient Lij that instead of being okay, one L12, this is going to be, so sorry, L22, L33. So I'm saying, okay, I impose this component. I do not know what this component is going to be. So this is how I run this test. But I'm saying that the shear components, they are all zero. They are known. They are zero. Now I could have said, okay, I don't know what L12 is going to be, but then the condition on the sigma is that sigma, I don't know what this is going to be. This has to be zero. This has to be zero. This has to be zero this year. And then these other ones, I don't know what they are going to be. So you can play with the boundary conditions depending on play. You can adapt the boundary conditions to the type of test that you are doing, and in this particular case, to the type of, yes, if you have a very short gauge, then the shoulders will force it to remain parallelepipedic. If it is a very long gauge, once you are away from the shoulder, in all this region, it can shear. So those conditions you can kind of reproduce by changing the boundary value problem in the code. Do you want to plot this, play a bit more, or should I start with the next topic? Have you run the simulations yourselves? Okay, the simple rolling. Okay, let's run the other one. So to run the other one, what I will do is I go to example 3 again, and this is going to use one of these files, Lij history, plane strain, or Lij history pure shear, or Lij history simple shear. Now the plane strain, of course you can run a monotonic test giving all the values of the Lij tensor. You can do that, except that in that case, all the components of the Lij tensor are enforced. You cannot say, okay, I'm going to leave some of these components free. Those are all enforced. That's the way that subroutine works. So the stresses are a consequence, but all the components of the formation are enforced. So the case is simple shear. Lij history simple shear is the one that we are going to run, which is the one that I showed you about only the first 4 lines, but it looks like something like this. It has 51 lines with a sinusoidal variation for the L13. So I go to rolling and simple shear. I go to this directory, copy the file VPSC8 in, and copy it into the root directory, VPSC8. And then go to the root directory. I'm going to delete the other output files. They get overwritten, but just out of caution, I'm going to delete them and run the VPSC8 code again, it is 0. So now this is performing the first 50 steps of the formation with the non-homogeneous velocity gradient. Then the yield surface, 32 probes of the yield surface. Of course, when you probe the yield surface, there is no hardening. You don't update the hardening. You just probe but don't update the hardening. And then 10 steps for the Lanford coefficient. Okay, we can look at the. I don't know if we are going to be able to see much with this, but we can look at the stress strain curve, stress strain file, stress strain dot out. So what are we looking at here? We are looking at epsilon. If you look at the component epsilon 1, 3, and I think that that's big. Yeah, in this case, the shear is imposed in the direction 1, 3, which is correct. The shear is in the direction 1 is the direction of rolling, 3 is the normal, so the shear is imposed in that direction. You will have to compare this with the other case to see what are the differences. But and maybe it is also worth comparing the activity file, how many systems you are using. And if you want to play with it, you can make the impose strain rate, increase the amount of shear in the strain rate. So instead of using, you will have to go change this file to put more shear in it, or put less shear rate or more shear rate. You can also put less plane strain rate and see what happens when you have more shear or less shear with the texture and the yield surface. But for that, one would need to go and change the file. So I encourage you to play a bit with this non-homogeneous deformation path and see how things change when you change the parameters of the run. Do you want to make a few runs yourselves of this problem and make a plot just to see what kind of Lanford coefficients come out for this particular case, just to plot the Lanford coefficients. Yes, or plotting the yield surface is slightly rotated with respect to this one. Maybe you want to plot to superimpose the two yield surfaces if you have the output files. Actually, the output files are in the subfolder, so you can import the output files from the subfolders and plot the surfaces against each other.
When we run both example 3, the rolling and the rolling shear problems, at the end there is a message which says the following floating point exceptions are signaling: IEEE underscore underflow underscore flag, IEEE underscore D normal. What does that mean?
I don't know. I have seen that, but it appears at the end of the run. No?
Yes.
Yes, and I really it's something of the compiler, but I don't know. It never was an issue, so I never bothered to find out really. But yes, it's looking for something that I guess it's looking for something that it cannot find. If it is a divide by zero, usually if you try to take the square root of a negative number, it tells you not a number. But if you want to use that in a simulation, it probably will stop and say, I cannot do this because this is not a number. Yeah, I don't know. You cannot certainly divide by zero. Some compilers assume that when you divide by zero, they give a value 1 to the result by default, which is dangerous because if you have a problem dividing by zero and the compiler doesn't tell you and assumes that it is 1, you may get completely erroneous result. But I don't know if that is the case with the GNU Fortran. Well, in principle, they should all be initialized. I mean, If they are not initialized, it's an error that we have made with the code. But in principle, all the variables should be initialized to something. Once again, some compilers may initialize them to 1, all the variables at the beginning, or to 0 at the beginning.
So I had one more question.
Yes.
In the stress strain plot, at the end of the plot, there are some points which are like stray points after the. I mean, they are. I mean, initially it's a straight line,
Yes.
but after some points, it sort of randomly picks some points.
In the
If
stress strain, what are you plotting in the
volumetric strain versus volumetric stress. So those are the first two columns, right? EVM and SVM.
Oh, the von Mises.
Von Mises, sorry.
The von Mises, do you have it handy there? The plot of the stress strain curve has some funny points, which are not linear. Now, the thing is, when I run the code and you calculate a process, be it a monotonic or a non-monotonic one, it writes this file. But but there is after the line 53, it writes also what are all the stress and strain rate components of the calculation of the polycrystal yield surface. Okay, so because you run the rolling, then you run a polycrystal yield surface, and then you run a Langford coefficient. So in the stress strain file, it gives you all the stress and strain components of all these three processes. And as you can see in the line 53, there, instead of the strain, what it's giving you is the strain rate. D is for strain rate. So it is giving you the 6 strain rate components, and together with the corresponding stresses. And then when you calculate the Langford coefficient in the line 90, it gives you also the 6 strain rate components and the 6 Cauchy stresses. If you just say plot this column against this column, you are going to get that cluster, which really belongs to another plot. It really belongs to another plot, because for the polycrystal yield surface, or for the Langford file, I only give the columns that matter. I don't give you all the stress and strain rate components. But if you want to know what they are, you look at this file. Okay. What tomorrow we'll do is work on the problem of torsion of a tube. It's not really a tube, but I'm going to explain why you can consider distortion of a tube with the fixed ends, with the ends fixed or with the ends free to. So tomorrow we are going to be working on this problem. That is also an interesting problem where the boundary conditions can change a lot how the material responds. Well, thank you.